In this video, we take a look at chapter 2.3, the inverse of a matrix. Our objectives for this chapter are to find the inverse of a matrix, if it exists, using Gauss-Jordan elimination, and then we'll also see how to use Sympy to calculate the inverse for us. We're going to use properties of inverse matrices, and then we're going to use an inverse matrix to solve a system of linear equations. So we say a square matrix, and we give it dimensions n by n, where n can represent any integer, is invertible, or we can also say non-singular, when there exists an n by n matrix that we call A inverse. So right here, this is how we denote our inverse in linear algebra notation, such that A times this other matrix A inverse gives us back the identity matrix, a square identity matrix that has the same n by n dimensions. And such that if we multiply in the opposite order, A inverse times A also gives us the identity matrix. So because our inverse works in both directions, that's why we have to have a square matrix. So any matrix that is not square is singular, not invertible. So we call A inverse the multiplicative inverse of A. A matrix that does not have an inverse, as we said in the last video, is called singular, or sometimes called non-invertible. And non-square matrices do not have inverses. So we're going to start by proving a theorem. So theorem 2.7 says if A is an invertible matrix, then the inverse is unique. So we're going to start by supposing that there are two inverses of A. So we'll start our proof by letting B and C be inverses of A. And we're going to see, can they be different matrices or not. All right, so since they're both inverses of A, then matrix B times matrix A is the identity, and matrix A times matrix C is the identity, because we can multiply here in either order. So then we could say, all right, well, matrix B is B times the identity, right? The matrix times the identity matrix of its same dimension as itself. And then we could replace the identity matrix with AC based on this calculation right here. So we're setting this in right here. All right, and then we could say, well, we can use the associativity property of matrices to say, well, that's just equal to the A times C. Just move our parentheses over since matrices are associative, matrix multiplication is associative. And then BA is just the identity matrix based on this relationship here. So then we can say, well, this is just the identity matrix times C, which is matrix C. So therefore, that implies, I'll use the double arrows to show that implies that matrix B equals matrix C. So the inverse of matrix A is unique. All right, let's take a look at an example. So we are going to find the inverse of this matrix A. This is a 2 by 2 matrix, and we're going to do it by hand, and then we're going to verify our calculations using Sympy. All right, so we need to solve the system AX equals I to find what the matrix X is that works as an inverse for matrix A to give us the identity. So we can say matrix A here times matrix X, which we'll call X11, X12, X21, and X22, so the location of all those values inside is the 2 by 2 identity matrix. All right, so this gives us 4 equations if we go through our matrix multiplication. We get 3 times x11 plus 5 times x21. We'll find this row by this column equals 1, the value from right here. And then the next equation we get is, if I keep going with my 3, 5 row, I get, I can multiply by this column, 3 times x12 plus 5 times x22 equals 0. And then if I take the second row by the first column, I get 1 x11 plus 2 x21 equals 0. And then multiplying by the last column with the bottom row, I get 1 x12 plus 2 x22 equals 1. All right, so we are going to put these into an augmented matrix here. And so the first augmented matrix is going to correspond with these values over here on the left side. So we'll have 3, 1 and 5, 2 columns. And we're going to augment with the column vector. I'm not going to close my matrix off just yet. I'm going to augment it with 1 and 0. And this matrix is going to correspond with 3, 1, 5, 2, 0, 1. So that's the augmented matrix constructed from these 2 equations. All right, we're going to go into Sympy and take the reduced row echelon form of both of those matrices. Let's see, I'll call them E and F. Verify matrix E here is matched to our first matrix. And then I'm going to call this next matrix matrix F. So to save some time, I'm just going to arrow up and swap out the last row values here. And then we'll print out matrix F. And here it is. So we can see these are the 2 matrices with different solutions. And then we want the reduced row echelon form here. So we are going to type, we'll do matrix E first. So we'll do E dot RREF, parentheses, and then we just want the first result, which is the reduced row echelon form of the matrix. And then we'll do the same thing for matrix F. And you can call your matrices any letter that you like as long as Sympy's happy with it. I just chose E and F for convenience and not to mix up with what we've already called matrix A. All right, so here are our 2 reduced row echelon form matrices. So I'm going to go back to my whiteboard and keep calculating with these matrices. All right, so I have the first matrix 1, 0, 0, 1, 2, negative 1. That's from Sympy. And then the second matrix is 1, 0, 0, 1, negative 5, 3. Also reduced from using Sympy. All right, so then A inverse is going to be the combination of these 2 augmented solutions here. So we get A inverse as 2 and negative 1, and negative 5, 3 in the second column, and we're calling this matrix X. So since the row operations performed to find the reduced row echelon form depended only on the coefficient part of the augmented matrix, we could solve all 4 equations simultaneously by using what's called a doubly augmented matrix. Sometimes we say, let's take matrix A and augment it with the identity. So this is matrix A with 3, 1, 5, 2 by the columns. And then we augment it with the identity matrix. And then we can put this into reduced row echelon form. And the result is going to be in the form of identity multiplied by A inverse. So let me show you how that would work out in Sympy. So let's head over there. Let's see, we'll call this one G. And it is in the top row, 3, 5, 1, 0. And in the bottom row, 1, 2, 0, 1. Those are my matrix. And then we can say G dot REF. And get the first object returned. And there you see identity matrix times our inverse. Now, you know, technology is even more efficient than this. We can easily code a computer to do this for us. So you can actually in Sympy even type A star to get that exponent representation, -1, except I didn't call my matrix A, did I? I don't know if I've defined matrix A yet. I gotta put matrix A in here first. So A is the matrix, 3, 5, in the top row, and 1, 2, bottom row. Oh, I left a bracket out there. So if you ever make a typo or a bracket left out, like I did, just arrow up and correct your entry. And we can verify, okay, here's our matrix A, and then we do A, exponent with the double stars, -1, and Sympy returns my inverse. If you try to do an inverse on a matrix that is not square, Sympy will give you an error and say, you know, it's not a square matrix, so you can't calculate it there. All right, in the next video, we're going to see some properties of inverse matrices and do some proofs.